Okay, the paper we're going to run through today is paper 6, the alternative to the practical. There we go. So this is the alternative to the practical paper, the one that you do instead. And this is May-June 2018. And the exam code here, 0625. This is paper 6-1. Alright, so let's start running through that now. Question 1. A student is determining the acceleration of free fall, g, using a pendulum. Figure 1.1 shows the pendulum, and figure 1.2 shows one complete oscillation of the pendulum. And first question A, on figure 1.1 measure the distance d. Alright, so what you'll have to do here is pull out your ruler and physically measure the distance. So put it up next to the drawing there and measure it. And if you do that, certainly in the exam you'd measure about a distance of 5.0 centimetres. Now, this is a key point. If you're printing off these exams and you're working through them at home, then what you'll find is the distance you measure will be slightly different. Now, I printed it off on letter size paper, and the distance I measured was 4.5 centimetres. If you print it off in A4, you might measure 4.7 centimetres. So when you print it off at home, you'll get a slightly different size to the one that they've printed off at the exam board and so sent out to the different schools. So just be aware of that. Anything that involves measuring the distance physically on the paper will probably give you a slightly different answer. No reflection on yourself, it's just the sizings will be slightly different. Right, now we're being told figure 1.1 is drawn 1/10 of the actual size. Calculate the actual distance d from the bottom of the clamp to the centre of the bob. Alright, well if it's 1/10 the size, then the actual size will be 10 times bigger. 5.0 centimetres times 10, which will give us 50 centimetres. And there we go. There's our answer. The student displaces the bob slightly and releases it so that it swings. He measures the time t for 10 complete oscillations. The time t is shown on the stopwatch on figure 1.3. There we are, 14.06 seconds. Write down the time t shown in that picture. Oh, well, there we go, nice and easy. Key point, 14.06 is wrong. Why? Because it's time. Put in your units. Very important. There's no point losing marks for something silly. All of the other questions so far, here we go, you can just see that at the top of the screen, has already got the units in it. This one does not. So it's key point there. Make sure you write down the units if they're not already in. Now, calculate the period t of the pendulum. The period is the time for one complete oscillation. Alright, so we're told that this one, 14.06 seconds, is the time for 10 oscillations. So the time for a single oscillation will just be that value, 14.06 seconds, divided by 10, which will give us 1.406 seconds. And again, you can see there's no unit there, 1.406 seconds. Be careful not to get caught out. Right, calculate the value of t squared. Well, you've got 1.406 was your value for t, so 1.406 squared. Put that into your calculator and you will get a beautiful value of 1.977. We're just going to record this to 3 significant figures. There we go. 1.98. Oh, no. Let's pay close attention here. We took the value 1.406. That was seconds. We squared it, so that gives us the value seconds squared for the units. So remember, write that in. In part 5, calculate the acceleration of free fall g using the equation g equals 20 divided by t squared. Alright, let's do that. G equals 20 divided by t squared, 1.98 seconds squared. Now, this will give us a value of 10.1. We'll get 3 significant figures here, we'll carry that forward. 10.1 seconds to the negative 2. They haven't actually given us a unit to put in the top, but what they have told us is its acceleration. Now acceleration has the units of meters per second squared. It's just something to be aware of there. They're not giving you the units, but so you have to know that the units are meters per second squared. 10.1 meters per second, -2. C. The student adjusts the pendulum until the distance d measured to the centre of the bob is 100 centimeters. He repeats the procedure and receives another, and obtains another value for t squared, 3.94. Excellent. On the dotted line above, write the unit for t squared. There we go. Well, same as before. T squared has a unit, seconds squared. 2. Calculate the acceleration of free fall g using the equation g equals 40 divided by t squared and the value t squared from c. So using that value for t squared. Right. Give your answer to a suitable number of significant figures for this experiment. So g equals 40, and we know it's meters, divided by t squared, 3.94 seconds squared. Alright, and if we put that information in, then we will get the value of 10.2 meters per second squared. 10.2 meters per second squared. Part D. Another student states that repeating the experiment improves the reliability of the value obtained for g. It is a good idea. Suggest 2 changes that you would make to improve the reliability. The stopwatch cannot be changed. Alright. So, and in this kind of situation as well, you wouldn't want to replace the stopwatch. The reason is they haven't said that anything's wrong with the stopwatch. Sure, it might improve the reliability, but what's to say you're not replacing a beautiful stopwatch with one that isn't as good? Ideally, of course, you could do it, but no, there's things you could do that are much more effective. Much more effective. Step number 1, increase the length. If you increase the length, it'll take longer to swing, which makes your starting and stopping of the stopwatch more reliable. The other thing you can do that works incredibly well is increase the number of swings, of complete oscillations. Let's write that down. So increase the number of complete oscillations. They are things that are far more important than changing the stopwatch. Nothing that you've been told so far has given you any inclination that the stopwatch is bad. It's just, if you like, because it's this kind of experiment, it's a perfect stopwatch. E. State 1 precaution that you would take in this experiment in order to obtain a more accurate reading. Okay, well, step number 1, you know what? Look at it at a 90-degree angle. That's tremendously important. Oops, 90-degree angle. Just goes as perpendicular. And another possible thing you could do, use a fiducial mark. Put a little sticky bit of paper, maybe onto the clamp stand so it's clearer when it's passing by. Alright, question number 2. A student is investigating resistance. She uses a circuit as shown in figure 2.1. There we go, we've got 3 resistors in series, an ammeter, power supply and a switch. She measures the potential voltage, potential difference, potential voltage. A. She measures the potential difference V1 across resistor R1 and the current I in the circuit. Figures 2.2 and 2.3 show the voltmeter and ammeter readings. Write down the readings on meters in figure 2.2 and 2.3. So let's have a look at them. Alright, this one at the side, here we go. So there are 5 marks separating 2 and 3, so each one represents 0.2. That to me is reading 2.2 volts. Remember your units, very important. And for current I, let's see, 5 in between 0.2 and 0.3, 5 between 0.3 and 0.4, we are 1, 2, 3 up, so that's 0.46 amps. Part 2, calculate the resistance of the resistor R1 using the equation R1 equals V1 over I. Alright, so nice and straightforward. R1 is then going to equal 2.2 volts divided by 0.46 amps, which will give us a value of 4.78 ohms. There we go. B. The student measures the potential difference across each resistor in turn. She calculates values for the resistance R2 and R3 of the resistor R2 and of the resistor R3. Interesting sentence. She records her values below. State whether the results suggest that the three resistors have the same value of resistance. Justify your statements by reference to the results. Well, I'm going to say yes. If you look at those values, they're all pretty close together. So within the realms of experimental accuracy, then yeah, it's entirely likely to be the same value for the resistance. So let's just write that down. Yes. I believe that this suggests the three resistances are equal. There we go. And justification, well, within the realms of experimental accuracy. There we go. Excellent. Let's look at part C. Calculate the combined resistance R of resistors R1, R2 and R3 connected in series using the equation R equals R1 plus R2 plus R3. Give your answer to a suitable number of significant figures for this experiment. Alright, well, pretty straightforward there. Let's add them together. R equals R1 plus R2 plus R3, 4.78 ohms. Ooh, let's jump back and check if we wrote down our value, our unit. Yes, there we go. Key point, write down the units. And if you ever panic in the exam, go back and check. It's not a problem. So R equals 4.78 ohms plus 4.75 ohms plus 4.81 ohms, which if I add them all together is 14.34 ohms. And looking at these have all got three significant figures. So I'm just going to use this answer to three significant figures. Over here, 14.3 ohms. There we go, remember your unit again. D. The student checks the results by connecting the voltmeter across all three resistors connected in series. Take the potential difference reading you would expect to be closest to the reading she obtains. Alright, so here we go. What we see basically in this situation, there we are, is something akin to this. She measures this voltage and gets a value for the volts. She measures this voltage, gets a value here, measures this voltage and gets a value here. Now if she was to measure the voltage across all three of them, then it would just be the value here plus the value there plus the value there. So given they're approximately equal, it'll be 3 times V1. There we go, this is 1, 2 and 3 there, but they're approximately equal anyway. E. Complete the circuit diagram in figure 2.4 to show the three resistors connected in parallel, the voltmeter connected to measure the potential difference, and a variable resistor connected to control the current in all three resistors. Okay, so the potential difference, the voltmeter has to go across the resistors. We get three resistors in parallel and a variable resistor too. So first things first, let's put in a variable resistor. one variable resistor. Now we have 3 resistors in parallel. 1, 2. Be careful here, make sure 3. Make sure that there are no gaps. For example, here I go. That would be marked wrong. These lines have to touch. You can't have any gaps between them. So when I'm bringing this down, I can't do this. I can't say, hey, you know what? That would also get marked wrong. I have to make sure that all the lines are touching so there's a genuine path for the electricity to travel. Any gaps like a millimetre or bigger, you're probably going to get marked wrong. Be aware of that. Make sure that all the lines touch. Alright, so now we want a voltmeter to go across all 3 of them. V. There we go. Problem solved. We've got a voltmeter connected across all 3 of them. We have our variable resistor and we have our 3 resistors in parallel. Question 3. A student is determining the focal length f of a lens. Figure 3.1 shows the apparatus. There we go, we have some illuminated object on the left, we have U and V, we have a lens, and we have a screen over on the right hand side. The student places the screen a distance d equals 70 centimeters from the illuminated object. He places the lens close to the screen and moves the lens slowly away from the screen until a clearly focused image is formed on the screen. He measures the distance u and he measures the distance v. He repeats the procedure for values of d of 75 centimeters, 80, 85 and 90 centimeters. Alright. Here we go. The readings are shown in table 3.1. Calculate and record in table 3.1 u times v. So you're just taking the values in the 2 sections. Here we go. So you take the values here and you're going to multiply them by the values here. So 22 times 48.4 is going to give you 1065. There we go. 1128, 1200, 1283 and 1334. There we go. So I'm just recording this to 4 significant figures. I've got 3 significant figures and 3 significant figures. I'm not going to record it to more than that. I think 4 significant figures, it looks pretty good. Certainly there's no point putting decimal points after that. The general rule for significant figures, certainly when you start hitting A-level and like, and A-level by the same people, CIE, is that for significant figures you should use the same number as the smallest number of significant figures in a calculation, or one more. So if you get 3 significant figures times 3 significant figures, then you could have 3 significant figures or 4 in the answer. If you have 2 significant figures times 4 significant figures, then you can have 2 or 3. So the same or one more significant figures than the smallest number of significant figures. That's the general rule. Part B. Plot a graph of UV in centimeters squared on the y-axis against d in centimeters on the x-axis. You do not need to start your axis at the origin 0, 0. Okay, that's good, and I'll tell you why it's good. It's because one of the sets of readings doesn't begin till 1000 and then only lasts till 1400, and the other one begins at 70 and lasts till 95. So we're going to want to put a little jump in the axis. Alright, so we've got UV on the y-axis and D on the x-axis. And we're going to plot this set of values in there. So UV on the y and D on the x. So this axis here will be UV in centimeters squared. Remember to put the units on the axis. Years ago, a student actually asked me, why is it that you put the units onto the axis of the graphs? And the answer is actually surprisingly straightforward. Just suppose you were doing a graph of cars per person, Well, how would you draw cars on the graph? You can't. They go on the road. Yeah, if you do pineapples, the number of pineapples that a person has, well, you can't put people on the graph. You can't put pineapples on the graph. But if you take, say, and I'll just write this down, if you take 5 cars, say one person has 5 cars, I don't know who they would be, and you wanted to plot that, cars per person, onto the graph, you can't put cars onto the graph. But if you divide by cars, then suddenly they cancel and you're left with a number, the number 5. So if I take the values of D and divide by centimetres, then suddenly I'm left with a number, and I can put a number onto the graph, and by labelling it I can see where it came from and also what it represents. Now we're being asked to plot UV in centimetres squared on the y-axis, so there we go, and D in centimetres on the x-axis. And as I said, we want to put a jump into the axis, and we do that with that little symbol there, that little jump. Now let's start putting our values in for UV and for D. There we go. So 1000 to 1400 for U times V on the y-axis. Now something that's quite important is I'm trying to use up as much of the graph as possible. The more of the graph I use up, the more accurate it is, the more likely I am to get the marks. The only reason I haven't done a big black line up the sides of the graph to represent the axis is purely for clarity, because we're doing this on a computer. Okay, so that's UV values in. Let's put in the values for D. There we go. And now what I want to do, of course, is plot the values from the table. There we go. You can see I'm using up as much of the graph as possible there. Alright, so what I want to do then is apply a line of best fit. There we go. It's travelling through the points. It goes through one of the points, doesn't go through any. Sometimes you might have a line of best fit that doesn't go through any points. And that's okay as long as it's as close as it can be to as many of the points. Now, what we're going to want to do is start putting in some values that we can use, or find a point on the line at the top and at the bottom that we can use, and that'll be to find the gradient of it in a little bit. There we go. We're going to use a point 69.5 and 1050. That's the point that the line of best fit goes through. So these points that you use should be on the line of best fit. There we go, and make sure that they're clearly marked. There we are. Now another way to do that, of course, is to draw big triangle lines, and that's a very good way to do it as well. So the points that I'm going to be using soon are very clearly marked and labelled on the diagram. Alright. Part C. Determine the gradient G of the line. Show clearly on the graph how you obtained the necessary information. Well, gradient equals change in y divided by change in x. Now that's fine, we've got our values there, we've written down the points. What we're going to do is put in the information from the points we labelled on the line. There we are. So that's 1400 minus 1050, which is our change in y, divided by 94.5 minus 69.5 in the x-axis, which will give us a value, or give us 350 divided by 25, which is a value of 14.0 centimetres. There we go. Now, the focal length f of the lens is numerically equal to the gradient g of the graph. Write down a value for the focal length f of the lens. Give your answer to a suitable number of significant figures for this experiment. Well, it's numerically equal, and looking for significant figures, I think 3 significant figures is rather good there. There we go. Now, so 14.0 centimetres. So we've got the unit there, we've got 3 significant figures, and we've got the value. Now, one of the questions, of course, is why centimetres? Why is that the unit that we're using? Well, a key point. Let's look at part D. It says the focal length f of the lens, so it's going to be in centimetres. There's another way we can do it though. We can look at how we calculate the gradient change in y divided by change in x. The units of y are centimetres squared. The units of x are centimetres. There we go. So that's just going to give us, they'll cancel out, and that will give us centimetres as the unit. So it's very important where possible to write down the units that we're using. E suggests two difficulties in this experiment when trying to obtain accurate readings. Alright, well, pretty straightforward. Number one, measuring to the centre of the lens, always an absolute pain. Not easy to do accurately. And number two, finding the exact position of the clearest image. You'll know yourself, you sometimes end up moving the lens backwards and forwards to get it clear, and it's a judgment call. Is it clear enough? Is it just right? That's our other one, finding the exact position of the clearest image. There we go. Let's move on to the next question. Question 4. A student is investigating the effect of double-walled insulation on the rate of cooling of hot water in a copper container. The student places the copper container inside a larger metal container. He is investigating the effects of the size of the air gap between the copper container and the larger metal containers. Plan an experiment to investigate the effect of the size of the air gap between the copper container and the larger metal containers on the rate of cooling of water. Well, that's interesting. Straight away, they're saying investigate the size of the air gap, so you'll need to record that. So it's good to identify things that you'll need to record as you're going through it. And it's also asking you to look at the rate of cooling of hot water. Now, the following apparatus is available: a copper container, a number of metal containers of different diameter, all larger than the copper container. Alright, a thermometer, a stopwatch, a measuring cylinder, and a supply of hot water. You can also use other apparatus and materials that are usually available in a school laboratory. In your plan, you should explain briefly how you would carry out the investigation. Alright, so it wants us to describe what we're going to do. State the key variables that you would control. Draw a table or tables with column headings to show how you would display your readings, and we don't enter any information into the table, we're not required to. And explain how you would use your readings to reach a conclusion. You may draw a diagram if it helps your explanation. Well, it probably will help me explanation, so let's just briefly talk through what it is we're going to have to do. Okay, so what this is asking about is this idea that we have, say, a copper container, and we're going to add water to it. The water is going to get colder, so we're going to need to measure the temperature of the water. And it's asking specifically about placing it inside other containers to see how it affects it. Well, the first thing that we're going to need to do here, of course, is to cover everything over with cardboard. So it's all about heat being lost through the copper container, through the walls of the container, and not evaporating off, or not through the large movements of convection currents. Okay, so we're going to need that. That's something we'd find in the lab, just cardboard. We can expect to come across that, so that's okay. And water in here. And of course thermometer. And our larger container. I'm just drawing this down. Container as just a quick sketch to show what it is we intend on doing, and that then lays the groundwork for us to explain it. Alright, so first thing I'm going to do is take my little sketch that I did up there and just do it again in a slightly larger way. Alright, so here we go. Draw the copper container. The copper container is going to be inside a larger metal container. We have our water inside the copper container, and we're going to have the thermometer there. Not the world's best thermometer, but it doesn't have to be. Then we have a clamp stand, a boson. Clamp stand to hold the thermometer off the base of the copper container to get a better reading. of all that, I'm going to put a bit of cardboard. Okay, and then I'm going to label it. So here, thermometer. Here, cardboard lid. Here we have the metal container. Inside here we have the copper container. Here, of course, we have water. What would the experiment be without water? Over here we have a clamp stand and boss. Alright, that should be absolutely fine for our experimental setup. Okay, so key points, what we're going to do? Well, we're going to need to be adding a fixed amount of water every time and placing that inside a copper container. It's a good idea if we do one that doesn't have the metal container as a control, so that'd be the one that we start with. Alright, measure a fixed amount of hot water using the measuring cylinder. Put the water into the copper container, then you want to place the thermometer into the water and use the clamp stand to hold it above the base. Now you want to place a cardboard lid over the containers. Initially, of course, for the one that you do as a test, it'll just be the copper container, but after that it'll be the copper container and the one that's surrounded by. And what you do is you start the stopwatch once the temperature is a fixed temperature, say 75 degrees Celsius, and you time it for 5 minutes and you record the end temperature. Now you should do this once when it's just the copper container with no other metal containers, and use that as a control. And what you want to do is repeat this, say about 5 times, with the copper container located inside in the centre of different metal containers, and measure and record the gap between the container walls, because remember, this is all about finding the effects of the air gap on how quickly the water cools down. Alright, so let's draw a table saying the kind of results that we want them to record and how to interpret that to see what has the biggest effect. Alright, so what you can see is we're recording the gap distance, the final temperature, and the change in temperature. And I've put one entry there. I've got on the left hand side I've got control container 1 through 5, and control, of course, will have 0 gap distance. Now, the key point is that the one with the smallest change in temperature is the best insulator. So that's all we need to write to finish this off. There we go. The arrangement with the smallest change in temperature is the best insulator. That's it. All done. There we go. Good job. Okay. So if you like that video, please feel free to like and subscribe. I'm going to try and add a whole bunch more past paper questions and like. If you have any questions about this, or if you have any past papers that you'd really like me to have a look at, just feel free to drop me a comment. Alright, you have a great day.